Hi, there's no audio currently.
Yeah, there is no audio.
So that's a typical XPS system you can see in most of machine, and the one we have actually from thermoscientific, so that's why it's called a thermoscientific instrumentation. So for this system, somehow the X-ray is installed at the bottom, so you can see the X-ray coming from here. It will generate some X-ray, and the beam will be going through the monochromator to do some filtering, and eventually the X-ray beam will be landing on your sample surface. And in most of XPS system, you also have an ion gun for etching and have a flood gun for neutralization. The signal that's coming out from the sample will go through some lens and eventually will go through the analyzer and detector. Everything you're seeing here actually housed in some high vacuum chamber. For XPS measurement, we're dealing with some electron, ions, all this particle is not going to be in the air. So you need to be housed in some ultra high vacuum chamber so you can get enough signal. So here just a slide show you what's an ultra high vacuum chamber. So I give you a table of different range of vacuum here. So if you're doing some fabrication process, most of the time you're working on low vacuum or medium vacuum here. So between 10 to the power minus 1, 10 to the power minus 4. And if you're working on some SEM or TM imaging, you might be working on high vacuum. So there'll be a 10 to the power minus 4 to 10 to the power minus 8. But for surface analysis, since we are very sensitive about any air molecule, any contamination, so we need working in the ultra high vacuum chamber. So that's typically between 10 to the power minus 8 to 10 to the power minus 11 torr. So by doing the measurement in ultra high vacuum chamber, we can remove any contamination on the surface, any air, any air molecule, water molecule you have on the surface. We're going to generate some X-ray, so that's why we need some high voltage, and also the ultra high vacuum chamber can prevent some arcing for the high voltage breakdown. And most importantly, by doing the measurement in UHV chamber, we can increase your mean free path for all the particles you are dealing with. By the way, there's another type of XPS machine called ambient pressure or near ambient pressure XPS system. That's pretty much the same idea here, but some configuration is slightly different. So for that type of machine, you actually can do the measurement in much lower vacuum here. But that's not what we're talking about here. So for all the machine we have in our lab is on the UHV chamber. And the first major component we're talking about will definitely be the X-ray gun. So how do we generate X-ray in our lab? So we just simply have some, here is a very simple cartoon here. We have a tungsten filament here, and we supply some high voltage to the filament. So at the very tip of the filament, you will generate some thermal electrons, and those electrons will be flying in high speed and bombarded to a piece of metal. So really depending on which metal you're talking about. In the old day, people have been trying for all different kind of material for XPS measurement. But nowadays, most of modern XPS machine, most of people just use aluminum or magnesium. These two materials have been chosen just simply they have much narrower line width, so they can give you a better resolution. But for aluminum, you can put more power to the metal, so that's why I see most of the people nowadays just using aluminum. Occasionally, you might find some machine that using magnesium. That just simply because they want to go for a little bit higher resolution. But you can see a line width for magnesium actually is a little bit lower than aluminum. But again, aluminum have much higher power. That's why you can penetrate a little bit deeper to your surface comparing to magnesium. But the X-ray coming out from X-ray gun here is not a clean X-ray bin, so we call it dirty X-ray. There's still a lot of junk in the bin, so we need to do some filtering, and that's why the X-ray bin need to go through the monochromator, which just simply is some kind of quartz crystal plane. So by going through the monochromator, we can remove some Brownstrown radiation. That's the main source of the X-ray beam you're getting when you generate some X-ray beam. And we can also narrow your X-ray bin line width a little bit more, so it's about 0.3 EV. We can remove some X-ray satellite bins, and also we can focus a bin much smaller. And now the bin will be hitting on your surface, and the signal will be coming out from the surface, from your sample surface, and go through the analyzer. So the analyzer we are using in the lab actually is the 2-stage. The first stage will be focusing your bin to the entrance stage here. So you are controlling the acceptance angle and maximizing the correction angle. And once you go through the second stage, your electron will be either accelerated or retarded depending on the energy. So we are using this formula here. So R1 and R2 just simply the physical distance for your analyzer here. And most of machine nowadays are using the hemispherical sector analyzer. So it's kind of like a round shape here. And it's a constant resolution. So at different energy, all the resolution is pretty much the same. Once your electron beam has been sprayed out over here, then it will be detected by the detector. The detector is just simply an electron multiplier. And we are doing the 2D detector, so it's just like a channel plate with a bunch of holes in the inside. Each hole is considered one single detector. So in our lab, we are using 128 detectors, so that's 128 hole on the plate here. So the electron, one single electron will go into your each single hole and multiply. And by the time it coming out here, the signal will be much stronger. And another component that's shown in the XPS system a lot will be the frog gun. Sometimes we call it charge compensation. And again, it will be very important if you're working on any insulating sample. During the measurement, we need to make sure your sample is grounded. But if your sample is non-conductive, you need something to help you to reduce the charging. So especially if you're working on any powder sample, polymer sample, or even some biological sample, those sample is not good in conduction. We need some frog gun to neutralize your surface. And so what the frog gun is doing will be, the first thing will be, you will try to backfill your chamber with some argon gas. So that allow argon molecule inside the chamber. And we also give you some low energy electrons and ion to neutralize the entire surface. Here I show you two data that's taken from a piece of Teflon. So the Teflon sample is purely non-conductive. You can see from the cyan spectrum here, that's the one with the frog gun turned on. Now we can find each pit nicely and try to identify which pit belongs to which element. But once you shut down the frog gun, and that's the data from the magenta picture right here, you can see now the pit shape the intensity is much lower, and also the pit position has been shifted. So when your sample has some charging going on, your entire spectrum is going to shift to a higher binding energy. So it will be very difficult for you to determine which pit belongs to which element. So for instance, right in the middle here, this high pit actually belongs to fluorine. But now you can see from the measurement without the frog gun, we can't even see the fluorine pit here. And it also become much broader. So that's why without any frog gun for insulating sample, you are not going to get any good data at all. Up to the last slide, I would say for the XPS measurement is a non-destructive measurement. But once you try to use the ion gun, it's going to be some damage on the surface. So we're going to do some sputtering, some people can etching, milling, whatever you're going to call it. But anyway, you're going to do some damage on the surface of your material. So then what does ion gun can be used? It can be used for some surface cleaning. As I mentioned earlier, most of the sample coming here definitely have some sort of contamination on top. And the most common contamination you're going to see will be some hydrocarbon contamination. So we might need to do some surface cleaning to remove the top layer and get a measurement from the clean surface. We can also do some depth profiling, so which means we try to do some scanning etching multiple times and try to see how your material has been changed in the Z direction. And for the most modern machine, it happened almost like 10, 15 years ago. Now people have been start using so-called dual mode ion etching, which means we can use either monatomic ions or cluster ions. So for our machine, we are using argon gas for both cases. So you'll be monatomic single monatomic argon ions and cluster ions to bombarding on your surface. So the main difference will be the cluster ion is much more gentle. You can see each atom, the energy is only between 1 to 100 eV. But for monatomic, it's much higher. It can go all the way up to 4,000 eV in our lab. So it can give you much higher etch rate, and you can etch much deeper, but it can also damage your surface much more. So that's why most of the time, if you're working on any dedicated sample, any biological sample, polymerase sample, any sample you want to preserve the chemistry on the surface, you can still go and use the cluster ion source to do the cleaning. For instance, in the past, we try to do some cluster ions cleaning on a piece of graphene. If you try to use a monatomic ion, you're going to damage your entire graphene, and you're not going to see any signal. But you can use a cluster ion to do some gentle cleaning on the surface and still do the good measurement. And here's some data taken from my colleague Austin and Drew. Both of them are not here today. So they are working on strontium titanium, and it's a single porous chip. So the sample size is almost like 1 centimeter by 1 centimeter. The main difference between these two measurements just simply for one piece of sample, we try to do some monatomic etching for 5 minutes, and another sample we're just using cluster source etching for another 5 minutes. You can see so these two images are the STEM image, and we can see those crystallinity each atom nicely from the STM image. But for the piece of sample using monatomic etching, right on top here, you can see a layer of amorphous titanium and strontium. So, but for the one with the cluster source etching, that's just a clean surface right on top. So it show you when we do the monatomic etching, we really do a lot of damage on the surface. So if you really care about those very top mono layer, 1 angstrom, 2 angstrom, then the cluster source etching might be a better candidate for you. And now we can start looking into some data for XPS. And before we looking at the data, the first thing will be how we're going to correct the data. So here I'm showing you a couple of stages we have in the lab. So this guy is a normal stage we're using most of the time. And we also another stage in the second one here, that's called a tilting stage. And that's mainly for people who want to do some kind of angle resolve XPS measurement, which I will talk about a little bit more later. And the next stage, the following stage here is called a biasing stage. And the whole idea for using the biasing stage for XPS measurement will be you just want to do wall function measurement. And finally, the very last stage here is called a vacuum transfer module. That's for people who are working on some sample that's air sensitive. For example, we have a lot of people working on lithium battery here, and most of the time this material cannot see the air. So you want to load in your sample on the stage in some kind of grow box vacuum environment and transfer the entire stage with your sample to the machine. So your sample won't see the air during the loading and unloading. And when you do the measurement, there are really just two types of data you're going to get. So for XPS measurement, you're going to get a survey spectrum and also high resolution spectrum. High resolution spectrum just means some narrow scanning for certain element. So that's only two types of data you're going to get most of the time. So here is a survey spectrum. For one of my sample, very early sample, is a 10% palladium in some kind of carbon catalyst. So we do a quick survey, and that's the data you can see most of the time. And the first thing, definitely, once you get this data, you want to tell what kind of element you have. So we need to go and do identify which peak belong to which element. So you can see from the picture here, the very sharp peak right here, that's all carbon peak. Because we are working on carbon catalyst, so definitely we have a lot of carbon here. You also see the oxygen here and a couple palladium signal here and there. During the XPS measurement, the process to get the electron out will also generate some OJ electron, which we'll describe a bit more later. That's why you can also pick up some OJ signal here. So the O oxygen KLL, carbon KLL, palladium MNN, all these are OJ signal. Most of the time, they are not very useful when you're analyzing your XPS data, but sometimes you can also use those peak to see how it's shifting and maybe determine some chemical information. And then you take all this peak intensity, then we can get some kind of quantification. So based on the data you're seeing on the screen here, the machine calculator, we have almost like 92% of carbon, and the palladium is only 1.2%. But when we prepare a sample, this gradient should be 10%. So that's what's going on here. So the XPA data pretty much depending on three items. So the first item will be depending on photoionization cross-section, and also depending on surface sensitivity. And lastly, will depending on the final state effect. Because when we getting one or electron out from your surface, your entire system is not very stable. So you create a series of energy relaxation. So the data you can see is a final state effect. So again, the first dependent is the photoionization cross-section, which simply means we are calculating the probability for electron emitting out from its electronic state. So here a very simple picture from the we call it a Schofield cross-section. So in the early 1970, James Schofield calculated this table. So what we're looking for here will be here is the element atomic number. So depending on which element you are talking about, and here is the concentration, the cross-sectioning. So for instance, if you're working on a silver with atomic number 47, so look for 47 here and go up here. So you can see the most possible peak you're going to see if you're working on a piece of silver will be a 3D 5-half peak. But if you're working on carbon with atomic number 6 here and you go up here, you can see the most possible peak you can see will be 1s peak. So that gives you an idea which element and which signal you're going to see most of the time. And the second dependent is the surface sensitivity, and that pretty much has two parts. The first part is depending on your X-ray beam. So we know X-ray beam actually can penetrate quite deep. But since we are getting the photoelectron out from the surface, so you can mostly only pick out the photoelectron right from the top region of your material. The X-ray beam will attenuate quite a lot when X-ray going into your sample. So only a top portion of your sample can have signal moving out from the surface. And anything underneath, actually, we're not going to pick out any signal. The second component to determine your surface sensitivity is your inelastic mean free path. That's pretty much your sample dependent, depending on which element you're working on. So for XPS, and if you're using aluminum target, the aluminum metal to generate X-ray, the region we are detecting here is somewhere around this region. That's about almost like 80 EV to about 1,200 EV here. That's a range of energy we're going to detect for XPS measurement. And the next couple slides, I'm going to show you the final state effect. So the first final state effect you can see will be so-called spin orbital splitting. So again, depending on which orbital shell or electron you are moving out from your sample. So again, if you're working on carbon, so your the signal coming out will be from one S shell. So you're only going to see one single peak. That's why the carbon is only one single peak right here. But if you're moving the signal out from P, D, and F shell, you might going to see two peaks. So for instance, if you're looking for a gold sample right here, for the gold 4F signal here, actually you can, right now I can't zoom in here, but you can see double peak right here. And all these peaks have different ratio in area underneath the signal. So we will all these numbers here, we will need all these numbers here for the quantification later. The second final state effect is called multiplex splitting. What we're looking for here will be, so this guy is a mechanism sample 2+. So you can see we have 5 electron field on a 3D shell, but we only have one. If you're moving one single electron out from 3S shell, now this guy only one single electron in this shell, so you can either spin up or spin down. So that's why when you're looking for your data, you might see double peak. That due to the exchange splitting over here. And the next final state effect is called a shake-up satellite. So sometimes you might see some additional signal from your spectrum, which doesn't give you any information. It just simply some satellite peak. So, and you are going to see those satellite peaks very often if you're working on some transition metal. All this bunch of metal, if you're doing some measurement for this sample material here, sometimes you might see some additional satellite peak. So for instance, the data showing here is a copper signal. So this guy is a copper 2/3 main signal and 1/2 here. But you can see next to the main signal here, we also see some satellite peak here. Again, this satellite peak doesn't give you any chemical or any physical information. It's just some additional peak you can pick up when you're working on any transition metal. Earlier, I mentioned during the XPS measurement, you're going to pick up some OJ signal. And why do we go see OJ signal? That's what the cartoon is showing here. So again, if your X-ray coming in and knock out one of your core level electron, the system now is not stable. So one of higher level electron might fill in the low level electron, but it's still not very stable. So eventually, the outer shell electron here will be leaving your entire atom, and we call this electron as an OJ electron. Sometimes you can try to calculate your OJ parameter, which is written as an alpha here. That's simply the kinetic energy of this OJ electron plus the binding energy of this electron here. And by comparing the OJ parameter, again, you might be able to compare some chemical difference between your sample. But again, most of the time, we are not using this parameter for chemical analysis. And the very final state event we are going to discuss today is called the plasmon. So it's mostly happen only for material that if you're working on measurement on aluminum or magnesium, and if the surface is really clean, and when you do the measurement, you might see some additional peak right here. So for instance, this guy is an aluminum 2s peak. That's an aluminum 2p signal right here. But you can see next to this main peak here, there's a series of smaller shoulder peak right here with the same energy separation here. For aluminum, is around almost like 15 eV. So all this additional plasmon peak is not very useful. Just for your information, you might see this peak if you're working on a very clean aluminum sample surface. So that's our second data. When you do XPS measurement, that's so-called high resolution scanning. Again, people call it narrow scanning because you are only focused on very small range here. So this data is taken from the same sample, 10% palladium in the carbon catalyst. By doing the high resolution scanning, the whole idea will be you can do some kind of pip fitting. So you can do some deconformation and pip fitting. And you can try to determine some chemical molecular information. Again, XPS definitely is not the best tool for this kind of measurement. It really relying on how good you can fit your peak, so you can determine a different kind of chemistry. So for instance, for this sample right here, we see our pure palladium signal right here, but we also see some oxide right here with different oxidation states, so PDO and PDO2. So that's what people are doing when they try to working on any oxide here, and they need to determine the oxidation state. That's some data you need to correct and try to find out and do some good peak fitting. Again, if you want to get some nice molecular information, you probably want to go to my colleague Arthur, who have given a talk during the first week of the seminar. But depending on the sample you're working on, for instance, the metal cannot give you Raman signal, so you still need to come to the XPS and do some high resolution scanning and do a good fitting here. Again, based on your fitted peak, we can also try to get some quantification. So based on the signal we are fitting here, we have almost like 15. We only have 15% pure metal. The rest are all oxide here with two different oxidation state. So how does the XPS give you all this quantification information? So you can see the first thing we need to do, we need to substrate background. So when we working on XPS data, we only taking care about the area underneath your intensity. So we need a substrate background first. And there are different kind of mathematical algorithm you can use to subtrating your background. So mostly people will be using linear, Sherry, and Toga. They're just three different background subtraction people will be using over time. And over here, we are working with a thermoscientific machine. And they have another algorithm called the SMART algorithm. That's just simply an improved algorithm of Sherry. So, but again, Sherry is the most common algorithm people are using. The Toga algorithm is come up by a Danish scientist. And This guy, the Toga algorithm depending on some physical model, and also taking into account for the cross-sectioning for the energy loss. So, but unfortunately for the Toga algorithm, it requires a slightly wider range of scanning. So usually, it'll be more useful if you're working on some survey data. But for high resolution data, usually we don't scan all the way to 50 EV. We just scan maybe 10, 20 EV. We still need to rely on the Characterization algorithm. And once you substrate background, then we can go ahead and do some quantification. And here just a very summarize the formula how we try to do the quantification. And the formula is based on this the assumption, the cartoon right here. So we're assuming the signal you're coming out from your surface is about z distance from the surface, and the region we're going to detect is about dz. So the first term here is your depending on your electron energy analyzer, and the next two terms here is depending on the photo excitation. Over here, the exponential term here depending on the inelastic electron scattering, and the very last term here is depending on the elastic electron scattering here. So by plugging all the number we get from the machine, then we will be able to generate all the quantification information for your sample. So when you're working on XPS data, definitely the first thing you're looking for is those peak, so you know what's going on, what kind of element you have, so you can do some quantification. But a lot of time, the background signal, also the peak shade, also can give you a lot of information. Here is some data from the paper here. So the measurement is on piece of copper, but you can see the signal is coming out from different region of your surface. So the sample A here is right from the top surface, and sample B is from one side of the surface. Sample C is somewhere in between here, about 2 to 3 nanometer below the surface, and sample D is much deeper, about 2.5 nanometer below the surface. So when you go ahead and do the measurement, high resolution scanning for the copper signal, you can see the intensity, everything looks pretty much the same. You can't differentiate anything at all. But looking at the background here, you actually can find out which region of the sample you are actually detecting the signal. So you can see from sample A, right from the top surface, that's very, very low background signal right here. But if you pick out your signal much deeper, now you can see there's a lot of background. So that's why when you're looking at your XPS spectrum, if you see there's a huge background signal next to your main pit, which means we know your signal actually coming from somewhere much deeper inside your sample. Or maybe there's some layer of contamination on the surface, and that can also generate all this high background signal right here. And we are using the shifting of each pit to determine some chemical information. And that's pretty much using this point charge model right here. So your initial energy depending on the weight charge around the sample, and also the environment between the electron you're detecting. That's how the energy can be shifted according to the chemical information. So simply, if you try to withdraw some valence electron out, such as oxidation, you're going to increase your binding energy. But if you try to add in some additional valence electron to your atom, you're going to decrease your binding energy. Here is a very simple table. Show you a couple binding energy for the carbon functionalization. So for XPS, we don't have enough resolution to differentiate between a CC bond and CH bond. So they are all lumped to one single piece. So that's why it's sitting around 284.8 EV. But if you try to function your carbon material surface with some nitrogen and create some anion functional group, you can shift to around 286. And again, if you try to oxidize your carbon and create some kind of carbon double O bonding, now you can shift to a 288 EV. So all this energy shift is pretty much fixed. That's how you can compare your data to some database and try to find out what kind of chemical information you have. So now we can go ahead and look for a couple application for XPS measurement. So in contrast to the EDS, which you're going to hear the talk a couple of weeks from now from my colleague team. So EDS mostly only working with a conducting sample. But for XPS, we can working on both conducting and insulating sample. So here is some polymer sample. Actually, the sample is just a piece of PET. And we go ahead and do the high resolution scanning for carbon and oxygen. And you can see all the additional peak right here. All these peak belong to carbon, but with different binding energy. So depending on what you have. So the first yellow peak you're seeing here, that's a carbon CC-CH bond. Right here, around 286, that's C single O bonding. And right down here, C double O bonding, that's around 288. So you can try to refer the signal you're correcting here back to your chemical structure. So I mean, if you're looking for your oxygen peak here, now you can see there are two peak over here. One is belong to carbon oxygen double bond, and one is single bond here. So that's how we can determine different chemical information. You can also use XPS data to determine some thin film thickness. And yeah, we have a lot of people working in our clean room, and they making multiple layer thin film. Sometimes you're not sure what's your thickness for each layer, so you can come here to the XPS measurement and using some simple model as shown here to determine how thick you have for each layer. So the cartoon here just simply a very simple substrate, the silicon substrate. On top, we coat it with some titanium nitride film. So when you do the measurement on your substrate here, all the signal coming out from your sample is just a silicon signal. And if you go to some very thick region, somewhere anything beyond 10 nanometer, everything you're detecting here is just simply titanium and nitrogen. But in between, you can see a mixture of different signals, silicon, titanium, and nitrogen with different intensity. So by plugging all the intensity information here, we actually can go and determine how thick you have for each layer. In our system, we can create a model up to like 3 level. So you can, if you have 3 layer thin film coating on top of your substrate, we actually can go and create some model based on 3 different coating on top. And earlier I mentioned we can use a sputtering gun to do some depth profiling, and that's one example here. So this guy is the sample is a so-called smart glass. So which means you can keep your house warm during the winter time and keep your house cold during the summertime. And what's so special about this glass will be on top of the glass, actually there are multiple layer coating on top. And you can use XPS to determine each layer, how thick is each layer and what kind of material for each layer. And sometimes also try to see any additional information in between layers. So for instance, for data here, you can see on the top layer here, actually is some silicon nitride. And it only have almost about 15 nanometer. So the top layer is only about 15 nanometer. And now we start to see some tin oxide. And below tin oxide, we see some silver. So you can go through the entire state and eventually you just see your glass signal, so which means we have been etched through the entire state of the thin film. So that will be very useful if you see something unexpected. So this data is taken a couple years ago, and we are working on some integrated mid-infrared photonic chips. So we need to build some waveguide, the silicon waveguide on top of aluminum nitride thin film. And during the fabrication, we are not going to expecting anything between the silicon waveguide and the aluminum nitride thin film. But when we go ahead do the depth profiling, starting from the top silicon waveguide here, we do see some oxygen between the aluminum nitride and the silicon substrate here. That later we find out actually there's some kind of impurity oxygen gas during the deposition for aluminum nitride thin film. So but before you go and do a measurement, do the long depth profiling, we need to etch through the entire silicon waveguide and aluminum nitride here in order to see the interface between the aluminum nitride thin film and the silicon substrate underneath. So as far as I remember, this etching took almost like 24 hours. It's almost like 120 nanometer thick. So we need to go through multiple layers and finally go to the interface layer here. And we can also do depth profiling using argon cluster source. Earlier I mentioned the cluster source is give you much gentle etching, so which means the etch rate will be much slower. So this guy is again the PET sample, but on top of PET sample we have some fluoropolymer coating on top. So again, the signature for the fluoropolymer coating is the fluorine. So that's why we go ahead do some measurement and etching using cluster source. Right at the beginning, you see there's a lot of fluorine signal and some carbon and some oxygen here. And after a couple seconds, almost like 400 seconds of etching, Now you can see this fluorine started going down. So eventually, what we're seeing just carbon and oxygen, which means we reached our PET substrate here. So all the coating have been removed. So so you can also use cluster source for etching for the depth profiling, and that'll be very useful for this kind of very dedicated sample and dedicated coating thin film. When we talk about the stage, I mentioned that we have one stage that's called a tilting stage, and that's the one for you to do some angle resolve XPS measurement. So why do we need to do some tilting on the sample? When we do the XPS measurement, the typical sampling depth is about 10 nanometer. But what happens if you want to reduce the sampling depth? For instance, if you're doing some kind of monolayer cell assembly coating on the surface, your coating is only about 1 angstrom, 2 angstrom, and you want to pick up most of the signal from your coating, not from your substrate. In that case, you can do some tilting. By do some tilting, you're changing your takeout angle, so you can reduce your sampling depth. So here, just a very simple formula about how we can change the sampling depth here from 10 nanometer or up to maybe just a couple, 2 or 3 nanometer. So that's a whole idea for doing some angle resolve XPS measurement, which means you just want to get signal mostly from your top region only. And that's one data that been taken by Thermo Scientific a couple years ago. Again, the coding is some cell assembly coding. It's only about 2 or 3 nanometer. And again, for this guy, you can't do some depth profiling. Build the depth profiling, going to remove your coating right straight away, so you won't be able to see any difference. So the only thing you can try for this kind of measurement will be doing some tilting. So we try to tilt the sample about 10 degrees, 20 degrees, 30 degrees multiple times. So for our machine here, we can tilt between 0 to 70 degrees, and that can pretty much give you an entire region of the top 10 nanometer of your sample. So you can see different signal degrees accordingly based on the structure, chemical structure over here. Finally, the substrate is a gold, so finally you just simply see a gold signal, and also the measurement for this guy is just to prove how the organic molecule is binding to the gold surface. It simply relying on the tire group, and the tire group, the signature is a silicon pit right here. It just simply between the coating and the substrate, you see some solver signature. So by getting all those spectrum, we can also do some kind of imaging. Some people call it mapping. It pretty much can give you understand your surface homogeneity and also uniformity. Here is a sample from the Mooney lab here. It's just a 2 pieces of hydrogel, and one piece of hydrogel we try to have some acrylic and lamine content inside, which means it's high in nitrogen and carbon. And the other piece of hydrogel we try to have some alginate inside, which means it's high in oxygen. And the student she tried to combine these two, try to put these 2 pieces of hydrogel together. And what she's hoping to see will be the nitrogen is going to slowly diffuse into the alginate layer here. But she can't see anything, so she need to get some data to prove it. So we go ahead and do some mapping for using XPS. So what she's doing will be she put these 2 pieces of hydrogen together on top of each other, and we try to do the measurement on the cross section in here. And here's a mapping for nitrogen signal, carbon signal, and oxygen signal. For carbon and oxygen, you don't see much difference. Just simply we have a lot of carbon on one side and a lot very few carbon on the other side. But for nitrogen, actually we do see some kind of gradient from one side to the other side. And she go ahead and do some theoretical calculation, and looks like the data we got here is almost at 1%, within a 1% error between her calculation and the measurement here. So we can see a nice gradient for the nitrogen signal diffuse from one layer of hydrogel to the other layer of hydrogel. We can also use XPS measurement to do some fan span measurement. Again, XPS definitely is not best tool for fan span measurement. a couple slides later, we're going to talk about UPS, and that will be a better candidate. But you still can use XPS, try to measure the valence band region, which means just simply a low binding energy region. Usually you can see between 0 to almost like 30 EV here. And for the valence band, it's mostly just give you some kind of chemical information. You're not going to get any elemental information from this region. So for instance, these two data is taken from two different polymer. So you can get different signature from different system. And earlier we say we have a special stage called the biasing stage, and that can help you do some wall function measurement. And the cartoon showing right here just simply illustrate how we do the wall function measurement here. So when you do the normal survey measurement, for a wall function measurement, we need to know what is your Fermi level and what is your cutoff energy here. But when you do the normal XPS measurement, your high energy cutoff region is being overshadowed by your spectrometer wall function. So in order to see this edge here, we need to shift your entire spectrum. That's why we need to do some biasing. So for instance, if you try to bias your sample by 10-fold, you can shift your entire spectrum to the left by almost like 10 EV. And by showing this edge here, then we can determine what is your Fermi and what is your cutoff energy. Then we can do some simple calculation. The wall function will just simply taking your photon energy and minus your cutoff energy right here. So for instance, the pure gold should have a wall function around 5.3 EV, silver a little bit lower, and copper is about 4.7 EV. So that's how you can do some wall function measurement using XPS. So back to CNS, what do we have here? So right now, at CNS, we have two XPS machines, and they are both coming from thermoscientific. The first machine with a model called K alpha plus. So this guy, we can only do XPS, but we also have a dual mode ion source. So you can do the etching either using a monatomic argon ion source or the cluster ion source. We also have a second machine with a model called Nexa G1, first generation. So this guy can do everything for XPS, but we also have a UPS here. And we also have a guy called RIOS, reflected electron energy loss. And the last one will be ion scattering. So this guy is a multi-technique surface analysis tool. For the UPS, we are using helium-1 and helium-2. And they give you much lower energy. So the whole idea for doing the UPS measurement is very similar to XPS. You are still knocking out some photoelectron out from the surface. But since we are using helium-1, helium-2, their energy is much lower. For helium-1 is around 21.2 EV. For helium-2 is about 40.8 EV. So you can see, compared to X-ray we are using for XPS measurement, is much, much lower. So by using much lower energy, now you are probing read on the top layer of your sample, and you are mostly only getting valence band electron out from your surface. So here is a cartoon to illustrate what all these four techniques can be done. So for XPS, again, you're hitting your sample with some X-ray beam and getting photoelectron out. For UPS, you're hitting your sample with some UV light and still getting photoelectron out. That's why this two measurement is called as a photo emission. For ion scattering, what we're doing will be you need to hit your sample with some much heavier ions. So the heavy ion hitting on the surface, and it's going to lose some energy based on your surface atom, and you will go back to the detector. So the same particle, the same incident particle hitting the surface, go back to the detector. And what we're doing will be simply measuring the energy before and after. Then we can understand what kind of element you have on your surface. For the RIOS, it's pretty much the same idea as a ion scattering, but the difference will be now we are not using ions, we are using the low energy electrons. So the same electron will be hitting you on your surface and scattering back to the detector. Different measurement can give you different information. It really depends on what you're looking for. And here just simply a simple table to illustrate what each measurement can do. So earlier you already know pretty much what we can do for XPS. For UPS, again, you can see the sampling depth is much shallower, so it's only 3 to 4 nanometer. And you're not going to get any elemental information for UPS, but you can get some electronic information and also chemical information. For RIOS, usually what you're going to get will be you can get some band gap measurement, and you can also quantify your hydrogen. If you do care about how much hydrogen you have inside your sample, that's pretty much the only measurement tool we have at CNS that can try to quantify hydrogen. For ISS, it still gives you some elemental information, but you can see the sampling date is only about 1 monolayer. So compared to XPS, now this guy, the ISS, some people call it LEIS, low energy ion scattering. Some people call this measurement is much more surface sensitive compared to all this measurement technique. So for ISS, you can try to determine your surface coverage. For instance, if you try to do some ALD coating, thin film coating on your substrate, and the coating is only a couple cycles, so maybe it's only like 1 to 2 nanometer. So we know it's not going to be very uniform on the substrate. So you can try to use an ISS measurement to see how uniform is your coating on the substrate. Here just give me some data from reals to show you how we can try to quantify hydrogen. So that's a raw data from the measurement. So this guy is just be a measurement on a bunch of different polymers. So PET, PTFE, so this guy is Teflon, polystyrene, and so on and so forth. And we're actually looking for this shoulder peak right here. So different material with different amount of hydrogen will have different shoulder peak right here. So we can go ahead do peak fitting on this shoulder peak, and you can generate how much hydrogen you have. So for instance, for Teflon, the PTFE, we should have no hydrogen inside. So it's 0 over here. And polystyrene has the most hydrogen here. So you can try to plot the data according to your theoretical calculation here. Finally, it come to almost my last slide here. So this guy is just a case study for some organic LED material. So it's a PFO. You have very strong blue light emitting material. And the coating is about 30 nanometer, a thin film, spin coated on the glass. And we need to determine the electronic property for this coating. So what you can do will be, first thing will be definitely go ahead, do some XPS measurement. You do a survey, see any contamination. Then go ahead, do some high resolution scanning for your carbon and determine all different kind of functional group. Then we will go ahead, do some measurement for reals and try to determine the band gap and so on. Then you'll go ahead, do the measurement using UPS. That's a typical UPS spectrum. So you can see we are not going to identify any chemical information, but from the band edge here, you actually can know where's your Fermi, where's your HOMOS, and where's your LUMOS. So then you combine, then you can try to determine how much energy has been shifting. Then taking all this data together, you can generate this band structure right here. That's for a lot of people working on any electronic material. They will need this diagram here to understand the property of your organic electronic. With that, let's come to the end of my talk. If you have any question, I'm happy to take any question now. Yeah, sorry about audio in the beginning. So I know those people at the beginning might not be able to hear it from the Zoom. And there's no question here. Is there any question from the audience?
Could you clarify and explain on the process on how you identify the peaks of an element, specifically on the surface scan slide?
Oh, yeah. So as I mentioned earlier, for all XP data, definitely you are comparing your data to some database. So both those peaks are fixed. For instance, carbon CC bond should be always 284.8. So definitely you do the measurement, then you go and check your data, see is at 284.8 EV, do you have the carbon peak? Then you also do the same thing for each element. So usually nowadays there's a lot of program out in the market. You can just click a button, you'll go and identify all those peaks for you. But sometimes you might also need to identify those peaks manually. But just simply compare your data to some database. And also that's how you try to determine chemical information. You want to see how your peak has been shifted from its original energy position.
For my product, it's just about like the monolayer graphene.
Yep.
As user, can you explain like I remember there's a part like you mentioned low energy some.
Right, let's call it, we try to do some surface cleaning. As I mentioned, when you come here, bring a sample over here, and your sample is not under vacuum, so sample have been sitting in the air for some time. So definitely when you bring a sample here, you're going to see a lot of contamination. As I mentioned, a lot of time the contamination you're going to see will be just some hydrocarbon contamination. For instance, a lot of people working on some metal and they're hoping to just see the metal signal, but you're not going to pick up any metal signal because that's just too much junk on top. So we need to do some surface cleaning. For the graphene, if you want to do some surface cleaning, we definitely need to use argon cluster source. We are using argon cluster source over here. At MIT, their machine, actually, they are using carbon C60 cluster source. It really depends on what your preference. And the argon cluster source will give you a slightly lower energy comparing to C60. So you just do some surface cleaning on the top region to measure everything is clean. So you can go ahead and start do the XPS measurement on your graphene. Especially if you do some functionalization on the graphene surface, and you might need to do some cleaning to make sure we don't have any foreign particle on the surface.
In the XPS machine, why does the beam curve before it hits the detector?
For the beam curve?
What is that? Why does the X-ray beam?
Oh, that's a whole process to try to spread out your electrons depending on its energy. So again, some energy will be accelerating, some electron will be retarding, depending on the past energy you're setting. So just like I did mention, the past energy. So when you do the XPS measurement, that's one parameter you need to set. That's called the past energy, and your entire measurement resolution is about 1% of your past energy. So when you say a past energy, and you will try to spread out your electron according to its energy. So that's why we need to have a long distance for the electron to travel and spreading out. And eventually it will be landing on the detector. Yeah, so here is a picture on my business card, the Harvard logo. So we do some mapping. So this guy, we didn't do any surface pretreatment. What we're doing just we go ahead, cut the logo out and dump it to the XPS machine and see what's the elemental distribution. So you can see actually from different color in region, you actually have different amount of information. So here's a mapping, the combined mapping for carbon, oxygen, and aluminum. So that's why some people call this guy XPS imaging. You can generate some image based on your chemical or elemental information. Yep. The hemisphere. Yeah, so that's the same question he's asking earlier. So that we just need to have a long distance for the electron to spreading out, so we can differentiate different energy from the detector. So that's why we use a hemispherical structure. So that just the setup for this instrumentation. All right. So we are all set here. Then again, there's no question online. So that will be the end for today's talk. You have one more question?
Yeah, the working function.
Yes. Right. So yeah, for wall function measurement, definitely the sample need to be conducted. So we need to do some biasing. So in the old day, we had some people working on some diamond. They do some functionalization, but the diamond is still not very conductive. So even though we try to do wall function measurement, we are not going to get any useful data. So once your sample is conducted, even partially conducted should be fine. So we need to do some biasing, and you can try to determine the wall function of your material. So the main criteria for getting a good wall function data will be surface. At least the surface needs to be conductive. All right. So I'll see you guys next week for next talk.
Okay, could this that you mentioned the claim? Well, like, will that happen in driver sort of particularly for the cluster?
It's going to be dry.
It's going to be dry.
Yeah, again, the whole mission is going to be the ultra high temperature. So everything is
So that's why a lot of time when you sample the image is dry. The sample is not very so you can teach the sample. We actually do some trial information.
Like the dryer we are using especially UV lights, right?
Yeah, if you are your sample, so UV light, you can use that for
For cleaning.